The first thing to get our heads around with induction is the logic behind it, because proof at the end of the day, it is logic. What it is it's a series of statements, which I say we link them using what we call logical connectives. Now that's no different to any other type of proof. All proofs are that. Induction though, first of all there's pieces to it. So there's some statement, what it is we're trying to prove. That obviously is important, because if we don't know what it is we're trying to prove, well, how can we go and prove it? Then in an induction, we look at just the first case and see if it works, sometimes called the base case. Then we generalize it and say, well, let's just assume then it's always true. So we'll assume it is true. Usually we use K. I suppose it doesn't have to be K. It could be any pronumeral you like. And then we go and use that assumption to go show that it actually is true for the next case. And this here is the way we write it in symbolic logic. This is basically what we're saying is we need two things. We need statement one to be true. And the other thing we need is this one here. SK implies SK plus 1. In other words, if SK is true, then we can say K plus 1 is true. They're the two things we need. And if we have that, then we can imply that, all right, well, yes, it's always going to be true for everything. So those logical connectives I've used there, that's our symbol for and that's our implication, or if-then statement. So how do we structure it? It really doesn't matter which of the two things you do first. Right? Remember, you just need the two things so you can then go and do the induction. Traditionally, you do the first case first. Seems to make sense. Now, step one, you don't have to write step 1, step 2, and step. But the first thing I usually do then is, okay, I'm going to prove the result is true for the first case. Now, in extension 1, the first case will always be n equals 1. In extension 2, we take it further. It doesn't necessarily have to be n equals 1. It might be something else as the first case. But extension 1 should be saying the first case is n equals 1. But just watch out, just in case someone decides to slip one in where it's not. Then the next thing I do is I make that assumption. I'm going to assume what it is that I'm trying to prove is actually correct. Basically, you just match whatever the condition is in the question. Okay? K is a positive integer will usually be the case again in extension 1. If I want to write that same thing in a set notation to save myself a little bit of time, and it is a very minor bit of time, but I would say something like this. Well, assume it's true for n equals k, where k is an element of or belongs to the set of positive integers. Now I will go and prove it's true for the next case. The conclusion to this, see this step 3, this is actually a deductive proof. So an induction actually has a deductive proof inside it. So step 3 here is the deductive proof. And because it's a deductive proof, we want to conclude it with an if-then statement. That if-then, if this is true, then I know this is true. And I've sort of written it backwards here, but it's saying the same thing. I'm saying, well, it's true for k plus 1 if it is true for n equals k. So basically the same thing. And then the final step is actually the induction. Basically it's where we pull it all together and we induce the solution. It's tying the things together. We say, hey, hang on, we went and proved it true for the first case, so I've got that bit. And hang on, I also, in my deductive proof, proved it was true for k plus 1 if it was true for k. So therefore, it must be true for everything by induction. I've induced the proof. Again, in set notation, I'd write something like this. Since the result's true for n equals 1, then it is true. So that upside down symbol means for all. For all n that is an element of or belongs to the positive integers, but again, by induction. Those last two words are actually quite important. You say, this is how I can prove it. I'm proving it by induction. Let's look at some. So the first type we look at are series types. So 1 squared plus 3 squared plus 5 squared, basically all the odd integers squared. We're saying that this would be the formula. Now, the very first thing you write down in an induction proof is what you're proving. I don't know how many times I've looked at induction proof and the first thing I see is, I'm going to prove it's true for n equals 1. And I'm just reading this proof and I'm going, well, prove what? How do I know you're right? You're just putting down n equals 1, but you're not telling me in what. Remember, that is on your question paper. I'm not marking your question paper. I'm looking at your solution. Your solution. Anyone should be able to pick up your solution and know exactly what you're doing. So you need to see that. That should be there. Don't be lazy. But now I'll say, okay, I'm going to try and prove this result is true for n equals 1. It's one of the rare times you'll see me actually write left-hand side and right-hand side. But in this one, it's kind of necessary because I'm saying, hey, if I work on the left-hand side of this, I get 1 squared, which is equal to 1. Now, you don't just say left-hand side equals 1. You show why it's equal to 1. So I've substituted into, well, effectively I've substituted into the general term here of 2n plus 1 squared, but 1 squared is 1. Now the right-hand side, again, I don't just write down 1. I substitute into the right-hand side and show that it is equal to 1. Okay, there it is, it's 1. And now I can make this bold statement. Oh, left-hand side actually equals the right-hand side. So hence I know it is true. Okay, I wouldn't actually write this down, I'm just highlighting. Remember there were the 2 key things we needed. I've got that bit. I've done that bit. So now the other part that we wanted. So I'm going to assume it's true for n equals k, where k is a positive integer. It's really important to define k, because that might be useful in your proof for some of them. The fact that it's an integer might be important for your solution. It might not be, but you basically just match what it is you're trying to prove. So I've essentially written the same thing down, but instead of n, I'm using k. That's what I'm assuming. But I now want to prove it true for the next case. Again, write down what it is you're about to attempt to prove. So now, again, it's that statement, but I substitute in k plus 1 for n, and I'll get this statement. That is what I'm now trying to prove. Okay, here's my proof. Now, for these series types, usually I'm going to start it off the same way. I'll rewrite that series as all of the terms, but I'll write in also the second last term, because that piece, sum to k if you like, that's our assumption. So I want to highlight, I'm going to substitute in my assumption. So I make sure it's there. And there is this extra term as well. Again, I wouldn't actually write this is sum k and this is term k plus 1. Just highlighting, that's what I've got there. But now I can replace that. You see, when it was just plus dot 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 plus, how can I play with the algebra of that? But now I've turned it into a nice piece of algebra that I can play with. And then I will usually say, hang on, how can I jump from this line to this line? How did I change? What allowed me to do that? So some sort of explanation on the right-hand side. Much as you would do in your geometry, which is a deductive proof. And this is what I'm saying here. This piece of the induction is a deductive proof. So it's no different. Just because it's not geometry doesn't change it. I write my reasoning down. Well, it's simply by assumption in this one. It's a nice simple one. Now, it might be obvious, but hey, it doesn't hurt to put it there to make it clear that that's what I've done. Now, we keep one eye on what it is we're trying to prove. That's the nice thing with a proof. We know where we're heading to, so we don't waste time. For instance, I notice what I'm trying to prove has a common factor of 2k plus 1. So it would be stupid right now to expand this all out and then refactorize only to come up with a factor of 2k plus 1, which is already there. So let's just pull that out straight away and play with what's left. There also is another hidden common factor there that you can't see, and that is the 1/3. I mean, it's there in that second bit because of course it's a third times 3. But again, looking at what I'm trying to prove, I see a third as a common factor. So I may as well pull that out as well. So I pull it out. Much nicer to play with this piece of algebra. No fractions. We all hate fractions when we're playing with algebra, so we can pull that out. And now we have just a nice little quadratic to factorise, which of course is where I can cheat because I know where I'm heading to. Ooh, I wonder what these two factors could be. I look at what I'm trying to prove. That's what it should be. Doesn't hurt to double check and make sure it does. 3 1's a 3. Yes, I will end up with 5. Okay, good. That is the correct factorisation. But I don't have to waste a lot of time thinking about what this factorisation is because I know what I need it to be. So I write down what I need it to be and then I just check and make sure, yeah, that is correct. Because if it's not correct, then I've done something wrong somewhere and I need to fix that up. So there is my deductive proof. I conclude it with that if-then statement, although I've written it the other way around. I've said, hence the result is true for n equals k plus 1. If it is true for n equals k, and that last bit is so important. You don't just write down, hence it's true for k plus 1. No, it's not true for k plus 1. It's only true for k plus 1 if it is true for k. That's what you're proving. You haven't proven it's true for k plus 1. You've proven it's true for k plus 1 if it's true for k. If then. That is the second part that we wanted. That sk implied sk plus 1. If sk is true, then sk plus 1 is true. That's the deductive proof. Now we tie it together. Since the result is true for n equals 1, that was the first thing we did, we've done our deductive proof, then I can easily conclude that it's true for all positive integers by the use of induction. There's our proof. And so yes, there's our conclusion that Sn, we have proven that statement we were trying to prove. Okay, let's try this one. This time the left-hand side's written in sum notation for us, which is nice, but sometimes you might like to write out the terms to get a feel for what the pattern is. Up to you, of course. And there we go. When I do write it out, I can say, oh, all right, what you're basically saying is 1 over, and then we've got the product of consecutive odd numbers. Okay, I'll go and prove it's true for 1. So the left-hand side, my first term, 1 over 1 times 3, which is a third. If I substitute it into the proposed formula of n on 2n plus 1, yes, I get a third as well. Okay, left-hand side is equal to the right-hand side. Hence, I know it's true. I've done one of my two pieces of information. I've proven it true for n equals 1. I will now assume the result is true. Now, whether you write down your assumption in sum notation or you write it in there, it doesn't really matter. But be careful when you substitute here into sum notation, because now the formula doesn't change. It's still going to be 1 on 2k minus 1 on 2k plus 1. It's just that the top changes, because you're not going to n now, you're going to k. You're still substituting into the same thing. And the right-hand side, yes, that would change to k on 2k plus 1. Now we'll prove it true for k plus 1. That is what I'm going to attempt to prove. Now let's do it. Again, it's a series type, so I will rewrite it, including the second last term, because that is my assumption, which I can substitute in nicely for. Let's do that. Okay, let's look at where we're heading. I need the denominator to be 2k plus 3. I've got an algebraic fraction here. Kind of makes sense to pull it into one fraction. That's what we're trying to prove, is all one fraction. Which means the first one now will be k times 2k plus 3. The other one stays at plus 1. We have a quadratic on top. Again, I don't really have to think too much. Mind you, the numbers are nice. 1's a prime. Well, actually, 1's not a prime. But it's only got one factor anyway. 2's prime. But looking at where I'm heading to, I kind of know 2k plus 1 has to be a factor, because I'm going to need that to cancel out to leave me with 2k plus 3 on the bottom, and the other factor is going to have to be k plus 1 to leave that on top. So yeah, there it is. Again, you can double check that that does work, and it does. The 2k plus 1's cancel, getting our required result. So yes, hence it is true for k plus 1. If it is true for k, and now I can pull it together. Well, since it's true for 1, got to be true for all of them through our use of induction. Okay, remember, basically there are 3 key parts to an induction proof. The setup, that's proving it true for the first case. Then you're going to assume what it is that you're asked to prove, and then you're going to state what it is you're trying to prove. So that's the setup. And there's the actual proof. And that proof is a deductive proof. Explanations for your non-obvious steps. Now, it might look obvious to you, but it needs to be obvious to anyone reading your solution. No, you write it down. Did I use a piece of geometry? Maybe I'd write that down. Whatever. And conclude it with your if-then statement. So you conclude your deductive proof. And then you tie it all together with that final beautiful statement, which goes, hang on, I know this, bingo, I've got it. Okay, let's start inducing.